So we're here for the second, I guess, or third, depending on your count. Final, in any case, morning of Sloppy. And we're going to start off this morning by a talk on speeding up pseudo-Boolean propagation by Rui Zhao, please.
Yeah. Hello, everyone. I will present this work speeding up pseudo-Boolean propagation. This is the co-author work with Robert, Albert, and Eric. I will start with some preliminary, and then I will explain the evaluation methodology, and I will show some improvements and a hybrid approach. Then I give the conclusion. We know that SAT technology has been used in different areas, such as the system verification, security, and mathematics, but there are some limits. For example, there is not a polynomial proof for some well-known problem, and there is also no natural encoding for some constraints. But pseudo-Boolean can be a remarkable alternative, and also we can use much more stronger reasoning procedures. And in the pseudo-Boolean solving unit propagation is very time-consuming. So the goal of this work is to improve the performance of unit propagation by careful implementation. So essentially, there is no novel algorithms. In pseudo-Boolean solving, there could be three types of constraints. The first is close. Then we will use to watch the literal schema. The idea is that if two no-false literal exist, we can guarantee there is no conflict of propagation. For example, we have this close. Initially, we are watching the two undefined literal. If later this becomes false, we can watch this one, and later this is false, we watch this one. Then if this is false, then we cannot find other literal to watch, so we have to set this literal to true. And during this process, we will keep one watch list for every literal which is a list of closes where this literal is being watched. So whenever one literal becomes false, we traverse all the closes in the watch list to check for propagation. The next type is the cardinality constraints in this form, and we need to watch k+1 no false literals. If we have a look at this example, what if we watch only 3 no false literal? For example, we are watching the first 3, and later, if the last 2 become false, actually we should propagate the first 3. But since we are not watching any of these 2 literal, we don't access this constraint. So in such case, the propagation will be not detected. The other operations just like closes here. The third type is the general pseudo-Boolean constraints. We suppose that every literal has one positive coefficient, and the left-hand side is greater or equal to the right-hand side. Then we can define this slack, which is the maximum number we can obtain from left minus the right-hand side. Obviously, if the slack is negative, we get one conflict. And for any undefined literal, if the slack is smaller than the coefficient, we must set this literal to true, because this coefficient has been counted in the slack. If this literal becomes false, after the decreasing, we get one conflict. On the other hand, if we can guarantee that the slack is greater or equal to the maximal undefined coefficient, we can guarantee this constraint is neither conflicting or propagating. But for the efficiency in practice, we would like to use the maximum coefficient of the constraint, because this value is fixed. We don't need to spend too much time on keep this value up to date, because as soon as one literal is added into the trail, this value could be changed. Now, if we look at this example, initially the slack is 2, which is smaller than 4 and 3. So we have to propagate these two literal. And later, if the assignment becomes this, slack is negative, we get one conflict. Note that in both cases, there could be some undefined literals. This is a big difference with clauses. So in the process, we need to keep the slack up to date. So all literals in every constraint must be watched. So we call this function, this propagation called counter-based propagation. So before the next slide, I would like to mention this RoundingSat solver, which is probably the fastest solver that we can find in terms of unit propagation in the literature, because it's the first one that precisely evaluates the different propagation mechanism, and we can understand that there are very strong evidence of design decision, and there is also the hybrid approach. We are going to improve the unit propagation in this solver. Here is the implementation of counter propagation in RoundingSat. We see that when checking one constraint, firstly, we check if the constraint is marked as deleted or it's not using PB counter. We do something else. And then we need to decrease the slack. If negative, we got a conflict. Otherwise, if this succeeds, we traverse the literal in the constraint to check if some of them can be propagated. Not that here, as soon as one literal is not propagated, then none of the rest of literal can be propagated because the coefficients are sorted in decreasing order. There could be one optimization. That is, for example, when this condition is not satisfied, we can save the position of the current literal, and later, if there is no back jump and the slack becomes smaller, we can enter this loop by starting from the next position that we saved. And if there is any back jump, some false literal could become undefined. Then we could start this loop from the first literal. Now, for the efficient, what about we use a watched propagation? The idea is just like a close. We hope to watch only a small subset of no false literal to guarantee there is no propagation or conflict. So we define this watch slack, but just considering the watched literal. So similarly, our goal is this one, and we also use the maximum coefficient for simplicity. If there are no enough watches, which means that we are watching all no false literals in the constraints. So at this time, the watch slack could be equal to the slack for counter. So then checking the conflict or propagation will be same as counter. Now here is the implementation. After decreasing the watch slack, if it's too small, we enter this loop to extend the watches. And during this loop, if one literal is being watched, we just set the positive coefficient to negative. Then in the end of this loop, if we have enough watches, we just unwatch the current literal by setting the negative coefficient to positive. Otherwise, if we don't have enough watches, the watch slack is negative, we got conflict. Otherwise, we check for propagation. Okay. If we want to improve the implementation of unit propagation, there will be one problem. That is, even subtle changes in unit propagation will have huge impact in the search space traversal. So this will blur the improvements. Look here. We run the tactical SAT solver on one single identifiable benchmarks by just shuffling the watch list using different seeds. Maybe we could expect that the solving time will not change a lot, but actually it's not the case. We see that the solving time and search space is very different. So in order to evaluate the improvements on the implementation, we have to force the solver to explore the same search space. So we can provide some additional information in the log file, and that could include the decision literals and the lemmas to be learned, and the clean up restart time, maybe something else. So when the solver can read this information whenever they need. So in our experiments, we will run RoundingSat on these logs for around 100 benchmarks. That's selected from the optimization category in this competition.
Can I ask a question?
Yeah.
So how much work is it to modify the solver to replay this execution, and how well-defined a format do you have? I mean, this seems to be almost something that you would have to, like, this would be super useful to have as a standardized replay format. I mean, because the problem you point out, that you change something, what you want to measure, but then the whole search changes, so you have no idea what you're measuring in the end. This is a huge problem, no? And it seems like a really nice solution. So maybe, you should have some kind of standard Pseudo-Boolean replay format that the solver should sort of support. But then the question is how much information do you need to keep to be sure that, Sat4j or RoundingSat or whatever, it could replay exactly this execution?
I think at least this information. For other information, for example, we could print some like the trail size, just for verify our propagation is correct. Make sure that all literals have been propagated. Yeah, actually, in our experiments, there could be a little bit more information just for debugging, but these are necessary.
Yeah.
Yeah, on the same line, if I may, I think this is very important, but just not for Pseudo-Boolean solving, for SAT, for MaxSat, for everything. So it would be nice to have sort of a standard log format that you can replay, and then that is extensible to whatever solvers we have. We can even think about, it's maybe more complicated for SMT, but something that we could reuse, and that would be sort of a new practice in the community. So this is really, really nice indeed.
I agree. Albert was saying something.
Yeah, so there's kind of a compromise here, because logs can be huge. Logs can contain lots of information. So in this work, what we try to do is to keep the minimum, to some extent, amount of information, so that would allow RoundingSat to reproduce exactly the same execution. And so, in addition, also a nice practice that Rui decided to do is to add some redundant information, so that you're making sure that you're exactly reproducing what you're supposed to be reproducing. Okay. So in general, my hope is this to be solver agnostic. Yeah. And the information we store is not, at least for one reason, it might be more, that here, for example, we say that we only write when a cleanup is performed, but we don't tell which clauses or which constraints are going to be removed in this cleanup. Because, if you use the same solver and it has exactly the same information and it performs the cleanup, you don't need to tell him anything else, because it's going to delete exactly the same constraints. But this is solver specific. So for it to be, solver agnostic, we should add some more information.
No, I'm fine solver specific, because that's fair. I just want to sort of the same solver.
Yeah.
It's
something that now we're working on it. So we're implementing it on the newest RoundingSat version. And the log format will be much more clear. It's more compact to some extent, and so on.
Because I agree also with what Daniel said. I'm wondering if I'm missing something, but I haven't seen this approach before. I mean, this should be a huge problem for SAT also, but with hindsight, this is such a nice idea, but I'm not aware that I've seen it being applied before, or at least not much. I mean, this is somehow the way it should be done, no?
Yeah, the thing is that unfortunately, this cannot be applied to any improvement you want to do in a solver. Yeah, but so the thing is, if you want to optimize performance, not just search space traversal, then that's the way to go. But unfortunately, if you will start improving search space traversal, which is, it's probably more important. Yeah, so that will not work.
Yeah, and since now I'm integrating this methodology in the latest version of RoundingSat. As I know, now there will be the linear search, but also the guided search. These two search may be combined at any time. So in my current version, there should be some more information about whether this in this time we need to use the linear search or guided search.
Yes.
Yeah. Yeah, now I will show the improvements. Okay, here let's see, this is one sentence from the source code of Capitol. It's well known in SAT that the most time-consuming operation of a solver is that when traversing the watch list, having to load the corresponding clauses into the memory, but these clauses could be very far from each other. So a lot of cache fault could be triggered. So our first step is to minimize the number of constraints loads. Here, we can see how data are saved in RoundingSat. For every watchlist element, there are two integers. For the second one, if the value is negative, we can use it to indicate the catch the literal of all clause. Otherwise, it's the index of falsified literal. And in the constraint, we use 1 bit for indicating whether this constraint is to be deleted or not, and another bit for specifying the propagation method, and the rest bit is for the size LBD, something else. And for this slack integer, we use the last two minimum value to indicate this constraint is close cardinality, or otherwise it's PB slack. This integer is for optimization. So again, if we look at the implementation, for the information highlighted in red, we know that they are saved inside the constraint. So already from the first instruction, we need to load the constraint into memory. But our proposal is to move some information outside the constraint. For example, in watchlist element, we could add the coefficient of the falsified literal and use the sign to indicate the propagation method. And also here we could know the constraint type. Inside the constraint, we can move this information into the 2 bits. And then we can move the slack and the maximum coefficient into this vector. You see the name means that slack minus maximum coefficient. And here we use 1 bit for the deletion infer, but later we will remove this bit. And now the information here could also exist in the watch list. So after this change, we can see that the green information is now come from the watch list, and only if after decreasing this slack, only if this value is negative, there is possible propagation. Then we start to load the constraint, and here we can get the precise slack. Then we check complete or propagation. So finally, we computed the percentage of this line that's executed. We can we get the average this percent and the median. They are very small, which is very good. Before the change, this percent could be 100%. But since there is more less impact for watch, because the information of whether this data is being watched or not is saved in the constraint by using the positive or negative coefficient. So the good impact for watch comes from here, the watch list. And also another good aspect is that when backtracking, we just need to access this vector to increase the slack. We don't need to load any constraints, PB constraints. So here we can see the impact of the change. So in such plots, we know that, for example, the points here are good and the points here are bad. The meaning is that, for example, for this concrete benchmark, the original system took 40 seconds, and our improved version is 3 times faster. It's more or less around 10 seconds. We can see that for counter, all points are good, and for watch, most of them are good. And for most interesting part is here, for the larger benchmarks, we improved a lot. So next step is to revisit the garbage collection frequency. We know that from time to time, some PB solvers have to remove some useless constraints from the database. In RoundingSat, these constraints are not removed immediately, but only when the wasted memory is large enough, then we apply the garbage collection. That is to reallocate the constraints and rebuild the watch list. So our suggestion is that we could apply the garbage collection in every cleanup phase, such that the constraint and watch list are more compact. And also, this bit in the vector could be removed. And so in the propagation procedure, all constraints are valid. So now we can compare the previous system with only one improvement with the current one that accumulates the both improvements. We can see that most points are good. And especially if we compare the scale, we can see that the counter propagation has been improved a lot.
So is it correct to say that the changes so far, the improvements, I mean, there are some points, I guess, in the bottom region which you don't want, but overall, the results are so good that this is clearly something that you want to do.
Yeah. So next step is about this watch list element deletion. We know that from time to time, some elements have to be removed from the watch list. If in RoundingSat, if, for example, if we need to remove this element, just copy the last one here and remove this one. But the problem is that the two positions could be very far from each other. Like in our experiments, if we have super long watch list, like it happens when we use the counter propagation. Accessing the last position could likely trigger the cache fault, but on the contrary, it will not happen here. In some self-solvers, you have 2 pointers at the, for example, you are reading from this position, and at the same time, you are reconstructing this watch list by rewriting the remaining elements. So the problem here exactly happened in counter propagation. So when we apply the change, we can see that most points are good. but there are not many for watch because it's the watch list is already very short. Since if we want to keep both type of propagation method in single system, and there are more good points, so we will keep this change. The last improvements on watch the propagation is this circular search for the watch literal. Since if one literal become false, we might need to extend the watch to guarantee this one no propagation or conflict. But there could be some inactive literal that in the end of the constraint that cause almost no work. If we always search from the beginning, it's difficult for this part to be watched. So our solution is like, for example, in this here, the numbers means the index of the literal. If we search from the beginning and stop here, then in the next time, we can start the search from this position. And in the end, if we still don't have enough watches, we can start from the beginning. But we need this second search only if there is one back jump, because some false literal could become undefined, so we can watch them again. Now this is the impact. We can see there are more good points. So here from the plot, we can see that in the original system, watch the propagation is much better than the counter propagation. Here they stop at the same point because we are running on the same logs, and with all improvements together, they behave very similar. So now we can use one hybrid approach. Yeah, this idea is proposed by RoundingSat.
Wait, sorry, could you go back again? So what are we?
Yeah, here in this original system, we are still running this system on the logs.
Yes.
Yeah, there is only unit of propagation.
I just say so actually like the old system is on the left and the new results are on the right. Is that?
Yeah.
Yes. Okay.
Yeah, the search space is completely same.
And what do we see from these plots? We see two things. We see that the new system is clearly better.
Yes.
And the curves also seem fairly close. What does this mean anything?
So the goal of this slide is not quite to show how good our improvements are, but rather to show that on the original system, it's obvious that the watches are much better than the counters.
Yeah.
Whereas after our improvements, they tend to be very similar.
Yes.
And that somehow reinforces the fact that the hybrid approach makes a lot of sense, because now we have two methods that are very competitive. It's not one of them is very good and the other one is so-so. Now we have two methods that are very good. Yeah. Okay. So it makes a lot of sense to push harder this idea of using a hybrid method in which you do not just use counters for all constraints or watches for all constraints, but you just decide per constraint.
Okay. Because there could still be huge differences based on the constraint.
Yeah.
So we'll use machine learning to tell us what we do.
Wow.
That's all one option.
Yeah, here sorry. So whenever you have a cactus plot of this type, the problem here is that you don't see the differences per benchmark. Yeah. So there are huge. There are cases in which just using counter or just using watches is a horrible idea. But overall, it's kind of 50-50. So that's the good thing about cactus plots, that it kind of smooths with this type of information that you don't want to see. Yeah.
So now we can decide to use counter or watch the propagation for every constraint when we are going to add these constraints into the database.
Oh, sorry, one more question. So maybe you don't have, sorry, but so if we would have a scatter plot instead with some kind of, different, I don't know, for different categories, different types, would we see like systematic differences, or is it unclear?
So if we compare the new system and we compare counters and watches, we will essentially see nothing. We'll see a bunch of points with you will not be able to conclude which of the two is better.
Yeah, no, but could you see like, oh, for this family?
Yes, you would.
For that family?
Yeah, so there will be lots of points, very low or very to the right.
Okay.
Yeah.
Yeah. Now we decide whether to use the counter or watch for every constant. So before we are going to add this constant to the database, we can compute the shortest watch to guarantee there is no propagation or conflict. We can find this smallest watch because the coefficient are in decreasing order. So, and then we can define this threshold from the comment line between 0 and 1. If the percentage of these watches are smaller than the threshold, we can use watch for the constant. Otherwise, we use counter. So in our experiments, we found that the best threshold is 0.2 in the original system, and there are this percentage of constraints are using watch. And also, we found that this hybrid system is much better than the system that use only one single propagation method on all PB constraints.
But just to, is intuitively, like, should I expect that if I have a constraint with a lot of different weights, some very heavy, some very light, that then maybe we will use watching, whereas if it's a cardinality constraint, then we will use counting? Is that what will happen? Or no, depends on the right-hand side, I guess. Sorry, yeah.
But so the weight, so it's not only the weights, it's the weights and the right-hand side. The combination of these things might tell you where. So the intuitive idea is that if you can watch a very few of them, then use watches. If you end up watching everything or almost everything,
you might as well count.
Yeah, it's much simpler.
Okay.
Yeah. And in our improved version, we found that these values become smaller. And this makes sense because we improved the counter a lot. So there are more constraints are using counter propagation. So here from the plot, we found that our improvements have left a much better system or hybrid system. And then even if we compare with this virtual best solver, this is a system that we can apply only counter on OPB constant or only watch on OPB constant. But this solver knows which is the best option in advance.
But wait, so what does that mean then?
Here, it means that if we just compare this improved hybrid system with the original hybrid system,
yes,
it's much better. You see, our improved hybrid system is much
I guess
faster.
what I don't understand, like what virtual best solver, like you could never be better than virtual best solver. I'm missing something.
Oh, virtual best solver is that we use only one single propagation.
One single propagation, but the best one.
Yeah, but the best one.
I got it.
And
okay.
for each benchmark, we know which one is the best.
Okay.
So last question is that whether these improvements translate to the overall runtime. So now we are not using the logs, just run the complete solver such that they can explore the different search space. And with this number of benchmarks, we can see that our final improved hybrid system can store much more instances. Now we have present this novel methodology for evaluating the unit of propagation, and by using it, And together with the careful implementation, we have improved the performance of unit propagation. For the future work, there could be different topics. For example, we could try to precisely analyze the impact of using this maximal coefficient of undefined literal. For now, it's not very clear. The next is that we could compute the slack with respect to the whole assignment. For now, we just compute the slack with respect to the prefix of the trail that's have been propagated. And the last one is that we can try to improve the hybrid system using different criteria. Yeah, that's it.
Thank you. Okay, I have tons of questions, but I thought maybe we can let someone else ask questions first, or if our virtual attendees have any questions.
Yeah, well, I mean, I have also a lot of questions. So could you go back to the watch literal deletion? Because I didn't really understand why. Yeah, and yes, here. So what exactly? Because the fact that you move, okay. So in the old times, you had 8-tail watch literals. So you were moving the pointers. You were always having the pointers moving, one from the beginning, the head, and one for the end, the tail. And then you had to move those pointers each time you have to propagate something, and you have to go back to move them when you backtrack. And so the watch literals had the nice property to not have to do anything when you backtrack. And the fact that you only watch the two first literals was a way to simplify the management of the watches, because in chaff, when you have those two moving pointers, you never know, which one you have to move to check that you meet again. So so if you're in counter-based, I do not understand why you have you watch everything for counter-based. So I do not see the benefit of doing watch literal deletion in counter-based.
I understand. Maybe you think that we are watching all literals in the counter-based propagation. Why do we need to remove?
Yeah.
Okay. The key point is that yes, for counter-based propagation, we don't need to remove any elements from the watch list. But don't forget that there is also clause and cardinality. The watch list element are in the same watch list together with counter-based propagation.
Yes.
So when we are visiting this watch list, perhaps this element is for the clause or is for the cardinality. We need to unwatch the current one, so we delete this element. But in this watch list, there could be some counter-based element. So it's very large. Yeah.
Okay. Oh yes. All right. So actually, it means that the benefit here is that it's a better management of specific data structure for clauses, kinetic constraints of PB constraints. I mean, I guess you have a lot of improvement if you have many clauses and a few kinetic constraints of Pseudo-Boolean constraints, for instance.
Yeah.
Is that correct?
Yeah.
Okay. And so I was wondering, because can you show the next slide, please?
Which slide?
Yeah, the next slide, yes, with the experiments. So I was, is it correct that mainly, so we see that it doesn't work for watch. And so,
Okay.
yes.
The reason is that in the original system, for watch, the watch list is already very short. So in the if we are using the original method, we just copy the last one to the current position. There is just one operation, just one copy.
Yeah.
So in the original system, this operation is already very good. But if now for watch we apply these changes, there could be many copy and writing, many reading and writing operations.
Yeah. Okay.
Yeah. So that's why for watch, the propagation is better to keep the original method, just copy the last element to the current position.
Okay. Thanks.
Yeah. And you see here for watch the propagation, the decrement, the performance is not decreased that much. But compared to the watch the counter propagation, we have improved a lot.
Yep. Yeah, I see. And I was just wondering, because you have you log everything, did you make scatter plots where you see for each problem how much time you have on each with each data structure, either counter-based original, counter-based improved, and because maybe it can allow you to cluster the benchmarks, and that would also this is maybe how you did the last part. When you need to decide which data structure works well. So the point is are there really families of benchmarks on which you want to use some data structure, or is it really, it depends? So if you have a lot of clauses and a few canality constraints or pseudo-Boolean constraints, you will, so the point is it important to really represent each constraint with a very specific data structure, or can it be done at the instance level? Could you just decide for one instance to use everything counter-based or watch-based, or do you want to really do it for each single constraint?
For now, we didn't distinguish which benchmarks we would like to use counter or watch. This is the general approach to be applied on all benchmarks. Yeah.
Can I clarify, Daniel? So if you go to the first slide of the hybrid approach. Yes, here. So the plot on the right, Daniel, what it shows. So when we say that we'll compare the improved hybrid with respect to the improved virtual best solver, this virtual best solver, that's exactly what you say. If I could predict in advance whether it's better to use counters for all constraints or use watches for all constraints, would it be worse than doing it per constraint? And the answer is yeah, it would be worse.
Okay, good. Okay. No, that's nice. Very nice. Thank you.
Any other questions? So one question from me would be, is there any chance that this would be, available for a current version of RoundingSat, a pull request?
Yeah, we are working on this version. And now I have implemented to produce these logs and read them into the latest version. And now we are going to start these first steps of improvements, and let's see how it works in the latest version.
I guess I realized that were you actually running this on the benchmark? You said so, I just didn't pay attention. So are these decision benchmarks only, or optimization benchmarks, or a mix?
Optimization benchmarks.
Optimization.
Yeah.
Yeah, and I guess also because like once you're playing around with how hard do you think it would be, like once you have this work already, if you wanted to also like start playing around with prioritization, say, propagating on cardinality constraints first and only propagate on clauses if you don't see anything else propagating? How would that be easy to integrate with your? I mean, there are many different things you could try. You could also try things like constraint deletion is something that we don't understand well. And potentially, if you have the notion of different types of propagators, one thing you could do is you could have like your hot constraints, and you could have your deleted constraints for the middle category of guys that haven't been helpful for quite some time. So I'm thinking about throwing them away. But maybe every 10th conflict or every 100th conflict, you give them a chance. Okay? So then you suddenly say, okay, now I'm propagating. Most of the time I'm propagating on the hot constraints, but every 100th conflict I propagate on all the constraints. But and then finally when it's time for database, and if constraint actually propagates from the non-hot category, then maybe you make it hot again. But when it's time for database erasure, then you look at the guys that are marked for deletion. They had a chance to be resurrected. They didn't propagate. Then you say, okay, now I commit. Now I erase them for real. Because we don't. There are all kinds of interesting things that you could do if you had more efficient propagation. I don't know if you've been thinking at all along these.
Yes, we're planning to do that, and we're happy to have you on board if you want to contribute. Somehow, because there, as you were saying, there are lots of things that could be tried when you have different propagators with different constraints. How to organize it? It's not obvious that just giving priority to. So you're saying generally that apparently if I have to believe Kuhlmann and Chai, it's like cardinality constraints are super.
I think that's what they say.
Yeah.
At the end, they claim like yes, that cardinality constraint. But I think we have. I think that is not true. For instance, for these. This came up in our discussion, the arithmetic circuit verification benchmarks. There it's pretty clear that you're going to deal with numbers. So your interesting constraints are actually going to be like sums, integers or parts of integers, and you want them spaced by different powers of 2. And there I think cardinality constraints would be truly terrible. You need to run the experiments to check, but I'd be very surprised. Yeah, very interesting. So, any more?
Yeah, can you go back to the cactus plot, or to these instances that like you didn't call cactus plot? Yeah, no, the previous one. No, the one that you just had before. This one, yes. If you would, maybe I didn't really get the point right, but if you would try to sum up in 1 or 2 sentences why counter-based. The improved version of counter-based is so competitive to watch. So why do they seem similar in performance here? So why is counter-based as good as watched?
I remember when in our improved version, since we reduced a lot of the number of constraints loads, but before. Since the watch list for the counter-based propagation is super long, so for whenever we traverse this watch list, the constraints must be loaded into the memory. But after we reduce the constraints loads, we did some statistic. We found that after the improvements, the number of loaded constraints for counter is very similar to the watch-based propagation.
Okay,
So that's why.
So it's more okay.
Yeah.
Or maybe we talk about
the constraints loads now.
So if you say okay, so the watch lists are kind of similar in length, and that's why they kind of like even up. Okay, good. Okay.
Thank you so much. Very interesting.